Hello everybody, welcome back to Fastware. So today I'm gonna be recapping what we've done with our memory allocator so far, and we will attempt to implement, or I'll attempt to demonstrate how I implemented actually the tests and the performance benchmark. It's gonna be pretty basic and we will expand it next time. So treat this as a summary of what we've done so far. So we created an alignment type T with the enum values for all types of alignments. We have a function that actually, given a size and alignment, aligns that size to next alignment. Checking a pointer if it is aligned. Our allocator API, where we, instead of returning a void pointer, we're returning a memory block which contains a void pointer, which is the space for you to put your data, and the size of the allocation. We created a stack allocator create info T, which allows us to create stack allocators using an API where it returns a generic allocator via the create function, given the structure of what type of allocator you want to create. We will be overloading the create function with different types of allocators to create, stack, pool, bitmap, and many different types of utility allocators that allow us to segment and segregate and choose what we want to do based on the type of utility allocators. Now we have a destroy function, destroying the allocator. Allocate, given an allocator and a size, allocates a memory block. Deallocate, you provide the allocator and the block to deallocate. The block must have a size. Now deallocate all will deallocate all memory, resetting the allocator back to its original state. And now we have a preferred size. So the API looks very similar to allocate. Now instead of actually allocating, it just figures out what size it would be good for this particular size. So stack allocator, if you have 17 bytes, but your alignment is 32 bytes, this will just return 32 instead of the 17 original. This is a utility function used in cases where you cannot store the size from the mem block in your calling function, and you need to discard it so you can retrieve it back because you always know the size that you used to allocate it. And owns, which does basically currently in our stack allocator, a range check if it's within the memory boundaries. So we went and we implemented quite a few bits. We implemented the create align storage, internal alloc, internal dealloc all, internal pref size, internal owns. The general basic principle is, given a generic allocator, we reinterpret cast it to a type, to an enum. Then we look it up based on switch, which currently is good enough. And we can then call the internal functions to actually perform the operation that we're looking to do. Now, of course, we implemented everything in one go. We didn't test anything. So I started today by writing some unit tests. And here they are. We're starting with the very primitive test, which is the stack allocator create, where we basically just give a structure with null as a parent. We want 1 kilobyte and align to 32 bytes. And we create it. We make sure that the allocator is returned, that it's not a null pointer, and then we destroy it. That's our check. That's the basic check that we do. I think you would agree that we all can figure out that this is the bare minimum that we need to do, right? Now the next thing is, of course, to check if we can at least allocate one block. So this is what it does. Just copies the first bit, and then it basically checks. If I give you 17 bytes to allocate, I expect a 32 bytes back because it's a 32 byte aligned storage. And I want to check if my pointer is 32 byte aligned, which that's what this particular check is. Passing this check, we want to continue to the next one, which we want to allocate all objects. So we know that we have 1 kilobyte. We know it's going to be 32 bytes per allocation, right? And then therefore we will go through all of them. We will check every memory block that it's 32 byte size and every block is aligned to 32 bytes. And then the last allocation of 17 bytes, which is supposed to return null PTR in size of 0, which that's what it does. Now using allocate all, so continuing with this pattern, so we check that we can allocate all, no more memory, we call deallocate all, and then we can repeat exactly the same process the second time with no problems. I think you would agree that testing the deallocate all here is quite important as well. Now, this particular test that I've written is a little bit more kind of a weird. It's testing this weird corner case for stack allocator that it cannot deallocate anywhere else apart from that if it's a last allocation that it was made. So following that, we allocate block, allocate block, allocate block, and then we deallocate the very first block. Now, expecting that when we allocate next, that the pointer will be further than the third blocks, which exactly what that assert does. Then we deallocate this block 4, and we expect that the next allocation will produce exactly the same block back as block 4, now calling block 5. So this particular thing that we've done, so here is our tests, and let's run them. It looks like every single thing succeeds. I didn't have to fix actually any bugs, which is surprising for me. I tend to make quite a few of them along the way, but this time it was actually quite successful. Now, the next important bit that we want to do is obviously produce a performance for this allocator. But in order to do so, first of all, what we need to do is start by setting kind of a plain, kind of a level playing field, right? The reason we want to have some way to measure how good our new allocator is in performing its task. So we start by measuring the system malloc, which is the fastest allocation that you get on the system, the malloc. What this does is we have a number of allocations that we will request, each allocation size, and then what we want to do is we look through a state. In our state object, we allocate that number of allocations, and because we only want to measure the malloc speed, not the free speed, we pause the timing and resume timing after we free every single allocation we made. So this little bit that I've added is so number of allocations times the number of iterations. It basically counts per allocation what is the speed of a single malloc call, basically. Using this, I produce different scales, the different basically sizes of allocations to see how malloc behaves under different conditions. The next one is to do the same thing with a system aligned alloc. So aligned alloc does aligned allocation rather than unaligned. And it can be slower, so we want to basically, because our allocator will always produce an aligned data back, if it's going to be a little slower than that but faster than this, maybe you can make an argument we still wrote a good allocator. But obviously we want to beat everything that system can produce. So what we do is exactly the same like a previous. We have number of allocations, allocation size, but this time we have also the alignment. We also store all the allocations in order to free them, exactly like previously, and recording per alloc time as well. And with exactly the same testing range and testing sizes and whatnot, exactly the same test will be performed here. Now the last one is actually our allocator, where we create our stack allocator. Here we basically align the requested size to the required alignment times the number of allocations to ensure that we have enough memory. We produce the alignment for the allocator. And what we do here is we just allocate block, and we're asking that block not to be optimized. So we basically allocate and forget about it. We call deallocate all instead of freeing each individual block, which is fine. And then obviously we destroy once we're done with everything. And then we call again these counters. So I think it's a decent test, and I would ask every single one of you watching to let me know in the comments if this is actually a good enough initial test, or I should have done something more better for both the unit tests and the performance benchmarks. But of course, here's the data and the time. There we go. Going to perf. Let's run and see how long this takes. It takes quite a few seconds to run. It's large data sizes, right? So we have system alloc, which we look here, it takes so about 4.5 nanoseconds to allocate a single thing. But now when we reach certain sizes, so this is 259 bytes that we want to allocate, this time goes way up into 20s and 30 nanosecond range. Now, aligned alloc is always a lot slower, starting in about 20s to 30s nanosecond range, and then going all the way here to basically 50 and even almost 80. Now, our stack allocator allocates everything starting from about 3, so twice as fast, and then dropping to about 3 times as fast as a standard malloc. And even at the very large sizes, we still maintain a 1.5 nanosecond per allocation, where in this particular case, we had already like 34 for standard malloc and 78 for system alloc. So while at small scale, small number of allocations, our allocator is only 2 times faster, only, than a standard malloc. At very large scales, which is where the actual allocators shine, how we allocate, how we do things, it's actually much, much faster. So we have X number of times that this particular implementation is fast. So with that, I would like to thank you for watching. And as usual, if you like something, please leave that like, subscribe if you have not, and tell me in the comments if what I've done is useful, if you understand what we've done. If I made mistakes, let me know about those. Code for tests and benchmarks will be available in the GitHub repository as usual, which you can find the link in the description. And have fun writing fast code. Cheers. Bye.